Welcome to another episode of Progress, Potential, and Possibilities, discussions with fascinating people designing a better tomorrow for all of us. I'm your host, Ira Pastor.
Welcome, everybody, again to another episode of our show. Today, bringing you another fascinating guest who has helped create a better tomorrow for all of us on some very unique fronts in the regenerative medicine space. And I'm really excited to say that not only do we have another guest from here in the city of brotherly love, Philadelphia, the biotech ecosystem here, but we're getting back with our friends across town at Drexel University and have the honor of being joined today by Dr. Kara Spiller, who is Associate Professor of Biomaterials at Regenerative Medicine Laboratory at Drexel University. Dr. Spiller received her bachelor's, master's, and PhD degrees, all in biomedical engineering from Drexel, where she conducted her doctoral research in the design of semi-degradable hydrogels for the repair of articular cartilage in the Biomaterials and Drug Delivery Laboratory at Drexel. She also did a collaborative work at that time in the Shanghai Key Tissue Engineering Laboratory, Shanghai Jiao University. After completing her PhD, where she received the award for the Most Outstanding Doctoral Graduate, most promised to enhance Drexel's reputation, she conducted research in the design of scaffolds for bone tissue engineering as a Fulbright Scholar in the Biomaterials, Biodegradables, and Biomimetics Laboratory, University of Minho in Guimaraes, Portugal. She also did postdoc work at Columbia. And Dr. Spiller is currently conducting some fascinating research in the design of novel immunomodulatory biomaterials, particularly in the area of bone tissue engineering. And she has broad research interest in cell biomaterial interaction, biomaterial design, international engineering education. A lot of really exciting themes to discuss today. Dr. Kara Spiller, thank you so much for taking the time to come on our show.
Thanks so much for having me.
It's really great to have you, Kara. I'd love to start off, as we typically do, by handing things over to you for a little bit. Obviously, bachelor's, master's, and PhD in biomedical engineering. Take us through the early story. Tell us everything about where you grew up, when you first got the interest in STEM, and why biomedical engineering, and a little bit of that early career journey. I think that'd be a great way to start off.
Yeah, absolutely. So I'm from Philadelphia, proud to be born and raised in the city of brotherly love. And, I was always kind of an arts and crafty kind of person. I was always tinkering with something or building something. And then in high school, I really got interested, I did well in my math classes. So I started taking harder math classes. So in senior year, I found myself in some pretty advanced math and biology courses. And when it came time to applying for college, I was like, well, what's the combination of math and biology, my two favorite classes right now? And that was biomedical engineering. But I had never met an engineer before. I had never met somebody with a PhD before. I didn't even know what a PhD was. So I really just kind of jumped in knowing next to nothing about what I was getting myself into. But when I started at Drexel, what I really like about Drexel as an institution and as an education university is the approach to hands-on learning. So I really started immediately building stuff and tinkering, and it felt right. Like I was channeling all my arts and crafts skills and all my, how I've always been kind of building something. I started channeling it towards something for the greater good, for actually building stuff that could have real use and utility someday, and particularly in the area of bettering human health. So I think I figured out pretty quickly that I had chosen the right major, even though I didn't know much about it. And I also started doing research really early at Drexel in the summer after my freshman year. And I loved research because I think I was attracted to that same idea of being able to use your little tinkering skills for something that has a larger purpose. But I also just loved the culture of it, which was very autonomous. You know, I was an 18-year-old with no experience, and yet I was in charge of a project. I was in charge of my schedule. I was in charge of designing experiments, getting the results, and then designing new experiments to follow up on those results. And I was just given so much independence and freedom. It was just really thrilling and exciting. I also liked that, you know, the vibe was very much just like kind of casual and fun, but like we're all here because we are interested in doing high level science. So I just loved it. So I just kept doing research. I did so much research as an undergraduate that it wasn't even a question about whether or not I would keep doing research as a PhD student, because I had done so much research as an undergraduate. That decision was never made. It just happened. Um, and then, but because I stayed at the same institution to continue to finish the PhD, I suddenly had like a huge amount of free time because I finished all of my undergraduate classes, but I was like already very good at research and still working in the same lab. So suddenly I was like, what should I do with all this extra time? So I started taking language courses as like a hobby because I could take courses for free as a graduate student. So I was taking Spanish and Mandarin Chinese because I always liked learning other languages. That was a hobby of mine in high school. So I returned to that as a first year graduate student, and I was just loving it. And then the Olympics were going to Beijing in 2008. And I was like, hey, I should go to Beijing because I've been studying Mandarin. It's a really fun language. So how can I get myself there? So as a student, I couldn't afford to just go to China on a trip, you know. So I thought I was really clever by designing a research collaboration with a lab in China that was very well known in the area of tissue engineering and biomaterials and regenerative medicine. And I thought if I did this, then Drexel would pay for my trip to China. And they did. So I thought that I was like tricking Drexel into paying for my vacation, you know. And then in hindsight, I now know that Drexel probably thought they were tricking me into being this like ambassador of Drexel, you know, in China. So it turned out to be very much a win-win situation. I had such a good time with that first research visit that when I got back after I did 4 months that first time, and my advisors in China were like, you need to come back for longer. You know, you can't do anything in 3 or 4 months. So I went back, and there was a doctoral dissertation enhancement program grant from the National Science Foundation, which I don't think exists anymore, but there's other programs through other government agencies that you can apply for. So I wrote a grant and got $15,000 to fund a return trip to Shanghai. And that was the most money I had ever gotten in my life. It was just to go live in Shanghai and pay my living expenses while I worked on this project. So living in China was a really huge life-changing event for me because, you know, I grew personally, gained confidence, all that stuff that you always hear about with living abroad and studying abroad. But what I was surprised about was how much it elevated the science to collaborate with people from such a different culture. Because we were two very different labs in two very different countries approaching the exact same problem from very different perspectives.
Yep.
Right. So the way that we are trained in the United States is ridiculously different from the way they are trained in China. And so just the approach that we took were so different. And I really think it was that clashing of perspectives that elevated the creativity of the science, because there was so much tension in every single experiment that we took like the best parts of the American approach and the best parts of the Chinese approach, and we ultimately published a paper that was more highly impactful than any paper either lab had ever published. So at that point, I was like, well, this is just fascinating, like the cultural side of things on affecting science. So around that time, I met a professor. I was at a conference in Korea, actually, and I met this professor, from the University of Minho in Portugal, and he was giving a talk about his research, but he mentioned that he really values international collaborations, so much so that he requires all of his PhD students to go abroad for at least a year. And I was like, what? You require that? That's crazy. So I thought I should go to Portugal and see and work in this lab, first of all, but, you know, travel around Europe, explore Portugal, and also learn what it is like to be forced to go abroad for a year, you know, especially, so, you know, when I applied for a Fulbright Fellowship, went over there and spent 8 months in Portugal. And so all my friends in the lab were leaving their families and their lives to go to Japan or Australia or the United States for a year. And what I learned about that was that it was they were really nervous about that prospect of doing that and picking up their life and doing that. But when their friends came back from their experience abroad, what it did was it created a culture where that's just what you did, and everybody had such positive things to say about it. You know, like it's not easy, it's hard, and it wasn't rosy and fun the whole time, but it was such a great experience. Everybody should do it. So that created a culture where that was an important part of the lab. So I learned a lot there. Then I did a postdoc at Columbia in New York City, which was even more international than the labs I've just mentioned that I did my previous training in. And so, and that work was also really creative. And I think the different approaches that were used in that lab was an important part of that as well. So when I started my faculty position at Drexel in 2013, I was like, I'm going to require my students to go abroad and do a little social science experiment on them and see what happens. So I don't have like a minimum time that they go abroad, but all of my American PhD students are required to go abroad for some period of time. And it's been great. So I've sent about 15 students abroad at this point over the last 9 years since I started my lab. And so I've got to visit them in some great places like Australia and Korea and the United Kingdom and Portugal and the Netherlands. So it's been awesome, and they, I think, have gotten a lot out of it too. So yeah, that's none of that was about science, but that's sort of how I view my identity. So I hope I answered the question appropriately.
Absolutely, absolutely, that was great, and I really enjoyed taking that journey with you. You know, Kara, well, we're going to be talking sort of about some of the core things you're doing now in terms of immunomodulation, immune system engineering. I wanted to just say, go back a couple of years, because I think, you know, the very interesting part of the story of everything you're doing now starts a few years before with your dissertation, as you were saying, where you focus on these hydrogels in the case of cartilage defects, and I apologize for simplifying it in this way, but in your dissertation, you really break down the biophysics of what's happening in these materials, looking at things like swelling and nutrient flow, waste exchange. Talk a little bit, if you would, say a few words, if you would, about your dissertation and some of what you learned then, because obviously we're going to be talking about all the stuff that is exchanged through these hydrogels in a little bit, but talk a little bit about what you learned there and sort of some of the aha moments when you were doing your dissertation. Said, hey, we got to look at some of these other things that are happening in terms of this collaborative concept, but we'll get to it.
Yes, totally. That's a great question, because there definitely was a pinpoint aha moment. Okay. So I'll tell you what happened. So my PhD was about making hydrogels, which are like polymeric gels, really, like Jello is a hydrogel. But the ones that I was making were synthetic, and they were designed to have cartilage-like mechanical properties. And that's like actually a very big challenge in biomaterials, because cartilage has very cool mechanical properties because it's mostly water, but yet it can withstand really high loads in your body. You know, I can't remember, this was now, I haven't done cartilage in a while, but it's something like 20 times your body weight are the loads that your cartilage actually withstands in your knee, but it's mostly made of water, you know. And then if you look at Jello, which is also mostly water, you can squish that without even trying, you know. So there's been a challenge in the field for a long time to make hydrogels that have similar mechanical properties to cartilage, but also kind of retain, that's it, just to make similar mechanical properties to cartilage. So I was able to do that with these hydrogels, right? The problem was the hydrogels being entirely synthetic, they were not, let's say, friendly to the cells. They weren't cytotoxic, so they weren't going to kill the cells. That definitely wasn't an issue, but that's like the bare minimum that you have to meet with a biomaterial. Cells need to like attach and infiltrate and stuff, right? So at some point in the middle of my PhD, I started worrying that this was not a good material to get cells to attach and to actually, like, so let's say I implant this thing in a cartilage defect, it's not going to work if it doesn't integrate with the surrounding tissue, right? So I started getting nervous about that at some point. And then a paper was published. And so the polymer I was working with, it was called PVA, polyvinyl alcohol. And in 2006, so I'm like 3 years into my research or something, I still remember the paper and the date. This paper comes out in a German language scientific journal. It was never published in English, in which they used PVA hydrogels to repair cartilage in humans. And this was crazy because this was like so similar to what my PhD was, and they were doing it in humans. So I didn't speak German at the time, but luckily one of my lab mates was German. So I'm like, hey, this title, and also German is just like weird English, you know, so I could tell that this was really important and I needed help in translating this article for my research. So my friend reads the article to me and he's like, yeah, basically they implanted it into humans and within 1 month, it worked great. The patients all reported decreased pain scores, increased range of mobility. But by 3 months, everything was worse. And when they did MRIs of those hydrogels in the cartilage, the hydrogels were just floating in fluid in this defect within the cartilage because there was zero integration with the surrounding tissue. And that was the aha moment where I was like, oh my God, all my fears have come true. First of all, that I was having this nagging feeling in my research that like maybe my research had a fatal flaw that I wasn't addressing. And then it was like proved in this paper. And I was like, how am I supposed to get a PhD now when these people just proved that it's a bad idea in humans, you know? But around that time, I was arranging this trip to Beijing and to Shanghai to work with Wei Liu and Yilin Cao, who are experts in cartilage tissue engineering, but on the cellular side, not on the materials side. So when I get to China and I like show them my hydrogel that I made, they were like, man, these mechanical properties are awesome. And I was like, I know, right? And they were like, but cells are never going to be able to integrate into this. There's not, the pores are not nearly large enough. There's nothing for it to attach to. This will never work. And I was like, yes, you were right about that. So with them, we came up with a way to increase integration with the surrounding tissue by like wrapping them in a polymer that we know that the cells would integrate with. And then so basically the project shifted from making ideal mechanical properties to trying to figure out how do you get cells to interact with a biomaterial in a beneficial way. So it completely changed my PhD. You know, it was no longer about the material, it was about the effects on the cells. So then when I wrote a dissertation about it. I don't think it's gonna solve cartilage someday, but I think that it contributed a lot to science. But ultimately, I don't think those hydrogels are ever going to be good for cartilage repair, right? But so it was a good learning experience. When I started my postdoc, I knew I wanted to focus on the cells by that point and say, how do we design a biomaterial to get cells to grow in, right? So I was thinking about, it was kind of funny. I wanted to change directions away from cartilage, but I didn't want to go too far. So that's when I switched to bone tissue engineering, because I was like, well, there's cartilage and bone in the joint, so it'll be not too difficult of a transition, right? Well, it turns out bone could not be more different from cartilage because bone is the most highly vascularized organ or tissue in your body, and cartilage is one of the only tissues that doesn't have any blood vessels, and that difference is huge because blood vessels are really hard. It's hard to get blood vessels to grow into biomaterials and engineered tissues. So basically I accidentally like completely changed directions in my postdoc. That was never really my goal, but I just kind of kept following what were the major problems in the field and trying to figure out how I could contribute some small piece to solving those major problems. So the major problem that I landed on was vascularization of biomaterials, which would be really important for bone, but really every tissue in your body except cartilage. So I started coming up with some ideas to how could I design a biomaterial to get blood vessels to infiltrate. And in my PhD, the strategy that was working well from the cartilage standpoint was sustained release of growth factors to attract those cartilage cells to grow in. So my idea for the bone tissue engineering was to make a biomaterial that sustained release of growth factors that would attract endothelial cells and blood vessels to grow in. So it really wasn't incredibly groundbreaking. A lot of other people had these same ideas, but you know, what I had in mind was novel, so it was worth doing, I think. But okay, flash forward. So now I'm in my postdoc at Columbia, and I have a twin sister who's a neuroscientist. Her name is Krista, and she was doing her PhD in neuroscience at Columbia at the same time that I did my postdoc there. In fact, that's why we both chose Columbia to do that part of our training, so we could live together. It was like sitcom twin scientists in the big city, you know, living in a 1-bedroom apartment, you know, commuting to the same building at Columbia. So it was great though, and Krista is a genius, and we would talk about science every night after we came home from our jobs in the lab. And I was saying that I was going to release these growth factors from my biomaterials to try to get the blood vessels to grow in for bone. And she was like, okay, are you going to do like a cranial bone defect in the skull, or are you going to do like a long bone in the arm or leg or something? And I was like, I'll probably start with a cranial defect because a lot of people start with that. It's easier because it's not load bearing. So most people kind of start with a skull defect if you have a novel biomaterial. And she was like, okay, because it just sounds like all of the growth factors that you plan to release from the biomaterial would affect with the inflammatory response and inflammation. And I was like, yeah. Where are you going with this? And she, being a neuroscientist, was like, well, I would worry about all that inflammation so close to the brain. Like, duh, you know? And I was like, oh man, that does sound like a big problem. And if you recall, a big problem in my PhD was that there was this nagging fatal flaw that I never addressed, and it kept nagging at me. Every presentation I gave during my PhD, a voice in the back of my head was like, this is a bad idea, it's never going to work because of that fatal flaw. But I kept selling it because that's what you got to do, you know? So I was like, okay, I'm addressing this fatal flaw head on. I am not going to let this nagging thing happen for my whole postdoc and my whole career, you know? So this was like week 1 of my postdoc at Columbia when this conversation happened. So there was another postdoc named Danny Freitas, who's now a professor at NC State in Gordana's lab at Columbia at the time. And I should mention here that my mentor at Columbia was Gordana Vunjak-Novakovic, who's one of the best mentors that anyone could ask for. And I recommend her for your show if you have not already had her.
Excellent. Okay.
Yeah.
I'll write that down.
So she was great at giving freedom to students and postdocs to explore their own ideas. And so in fact, that first day she was like, okay, so we'll meet next Tuesday and you'll tell me what your project was or is. And I was like, yeah, like I'm still figuring that out. Yeah, I kind of thought you were going to give me a project, but okay, no problem. Yes, Tuesday, I will tell you what the project is, you know. So there was this other postdoc, Danny. I knew he was working on the inflammatory response, and the primary cells of the inflammatory response are macrophages. So that's all I knew about his work. You know, it's still week 1 of my postdoc. And so I'm like, hey, can we chat for a second? And he's like, sure, what's up? And I'm like, okay, so I've got all these ideas for how to get blood vessels to grow into the biomaterials, and I'm worried that they are going to impact the inflammatory response. And he's like, oh, okay, good. We're on the same page. I was like, no, we're not on the same page. What page are you on? And he was like, the inflammatory response is so important for blood vessels that if you can control the inflammatory response, you can control blood vessels.
Yeah.
And I was like, whoa, that is crazy. And I love that concept. So I started reading immediately about the role of the inflammatory response in blood vessel growth and realized that it is a huge critical regulator, if not the regulator, of blood vessel growth. And not just blood vessel growth, all tissue repair.
Yeah.
And not just tissue repair, the success or failure of all biomaterials.
Yeah.
So suddenly I was like, this thing that I have been avoiding my entire education so far, the immune system, is so important. You know, I think the traditional approach to teaching biomaterials and training people in biomaterials was that the immune system was a really bad thing that we should avoid, and that if at all possible, you should inhibit the immune system. And can we even kill immune cells? That would be great. Like, that was sort of the training up until this point. And I realized that was fundamentally wrong. Like, the immune system is hugely important for, you got to promote the immune system for tissue repair. And there was a couple people in the field who were trying to make these points, I guess. Jim Anderson at Case Western, Steve Badalak at Pittsburgh. These were the people that I think already knew this, but by and large, most people, this is not how we were thinking in the biomaterials field. We were thinking the immune system was a bad thing. So I was like, I feel like I stumbled upon something that could be a game changer in the field of biomaterials and regenerative medicine and tissue engineering. So I pretty quickly designed a novel strategy to release cytokines from the biomaterial that would control the behavior of infiltrating macrophages, with the idea being that when you implant a biomaterial into the body, whether it's in damaged tissue or healthy tissue, that's an injury. And the first thing that happens is immune cells infiltrate that biomaterial, whether you like it or not. You can't avoid it. And if you try to avoid it, it actually makes things worse. But immune cells, and particularly macrophages, are very important for tissue repair. So my idea was, if we can control the behavior of those infiltrating macrophages, they will then in turn control all the other cells important for tissue repair and solve all our problems. So it was basically trying to go upstream of the process and control the controllers. And I thought this made sense too, because, I wasn't the first one to come up with the idea of releasing growth factors to promote angiogenesis, or the ingrowth of blood vessels. The problem is there's like dozens of growth factors that are released at very precisely controlled doses and timing in normal tissue repair. So it's literally impossible to engineer that system to have the correct doses and everything to make optimal blood vessels. But if you can go upstream and control the controllers, the regulatory cells, the macrophages, they know all of the correct doses and timing and everything of all the growth factors. You'll find I anthropomorphize macrophages a lot. It's the only way I'm able to talk about them. So that was the idea: control the macrophages, and they'll control everything else. So that's become everything we've been doing since then. Turns out macrophages are hugely important for the repair of every tissue, for response to infection, for diseases. So this has been an exciting area of research because it's allowed me to work on a lot of different things. So I actually never ended up doing anything too specific to bone. It's all been very fundamental to just tissue repair processes. The tissue that I became very interested in when I started at Drexel 2.0, my faculty position at Drexel, was chronic diabetic foot ulcers, which is an example of a tissue that should heal under most people. If you have a skin wound, it heals. But if you have diabetes, you have impaired healing, and sometimes it never heals, and sometimes it leads to an amputation. And macrophages and dysregulated macrophage behavior have been implicated as a major reason for that. So we started looking into, can we make better wound dressings using these principles? Can we modulate the immune system for better tissue repair? So there's a lot of ways to do that, and a lot of stuff in there. So I think that's going to keep me as an academic at Drexel for a long time.
Before we get to some of what you're doing in terms of the novel immunomodulatory biomaterials, I just want to go, because obviously the last couple of years, we've all heard so much about the immune system, both adaptive and innate, in the current pandemic. As you mentioned, you spent a lot of time with the macrophage, and this is a very unique cell, and in a sense it sort of straddles both worlds of innate and adaptive immune systems. Take us through, if you would, because I know a key part of what you're trying to influence, and we'll get to that in a minute, but is this very fascinating cascade of the steps that the macrophage takes, M1, M2A, M2C, and this cascade of inflammation first. We want to get rid of some of this dead cellular junk, lay down some new tissue. We got to get the cells there. And then third part, which is a really exciting area, remodeling. Hey, we need to put this cell here, that cell here in a certain structure. Walk us through a little bit about, because I think we think so much, oh, this is these cells floating around and they're killing some stuff, but they're doing a lot more, and the cytokines, the chemokines, everything else that they're spitting out and talking, cross-talking is extremely complex. Walk us through for a couple minutes about M1, M2A, and M2C. I think it's a very important part.
Yeah, so yes, this is really important, and this was another kind of aha moment that I had during my postdoc that really set the foundation for my research career. So when I started reading these papers, so this is like 2010, 2011, I'm a brand new postdoc learning for the first time what is a macrophage. I knew nothing about it. So what I was reading in mostly review articles, which of course are just summaries of other people's actual research articles, was that macrophages can take on two different phenotypes. So the macrophages are normally thought of as being this very pro-inflammatory phenotype, which is people started calling M1 because type 1 inflammation is the pro-inflammatory type of inflammation. Type 2 inflammation is like allergy and the response to parasites and stuff. So it's still inflammation, but it's very different than type 1 inflammation in terms of what are the consequences in your body. Both can be very bad if left unchecked, but both are, in the context of tissue repair, what these articles were starting to say at that time in the early 2000s and definitely in 2011 when I was reading them, was that macrophages must switch from M1 to M2, this type 2 macrophage, in order for tissue repair to occur. And chronic wounds that have impaired healing, they're characterized by super high levels of M1 macrophages for too long. And Steve Badalak at Pittsburgh and Brian Brown, they showed that biomaterials that were successful in integration with surrounding tissue had more M2 macrophages than biomaterials that were less successful. So we were starting to conclude M2 macrophages are great and M1 macrophages are bad because of those pieces of information there. So my very simple idea was to release cytokines from the biomaterial that promoted the M2 phenotype of macrophages, right? So I started, the problem was in the literature, again, still kind of review articles, there was a couple types of M2, particularly M2A and M2C. M2A, if I wanted to make M2A, I would release IL-4. If I wanted to make M2C, I would release IL-10. And the problem was I couldn't find any articles that had shown which one would be better at promoting blood vessel growth. And that was my ultimate goal, was to get blood vessels to grow into the biomaterial. So I just needed to know which of those two M2s would be better. So I started doing some simple experiments in vitro to say which one was more angiogenic, which one would promote the growth of blood vessels. And as I thought it was going to be a negative control, I included the M1 macrophages, the pro-inflammatory ones, just to show that they are not. I thought it was a negative control.
Oh, I see.
But what happened was those M1 macrophages, those M1 macrophages were the most angiogenic, and both M2 macrophages were not at all angiogenic. And I was like, wait, what just happened here? And it was highly reproducible. And then I just started, so I'm like, something's wrong here. This doesn't make sense. This is not what people are saying. And then I start to realize that all of this information that I had gotten was from review articles. And I was like, wait, let me check their references to go back to see who has anyone done like this experiment. So I go to the review articles, they say like M2 macrophages are angiogenic. So I go to their reference. It's another review article. And I'm like, it's frustrating. Give me the real article. So I read that review article. I get to the part where it says M2 macrophages are angiogenic. I get to the reference. It's another review article. And I'm like, dude, I need the primary research article. I'm trying to design an actual experiment here. I can't just go by your statement in this review article. So basically, I go on this long rabbit chase through review articles. There's like tons of review articles saying M2 macrophages are angiogenic, and they're all citing other review articles. By the time I finally get back to a primary research article, it's a tumor macrophage, and they say tumor macrophages, which are believed to be M2, are pro-angiogenic, and that's why tumors grow so much because of these M2 macrophages promoting angiogenesis and blood vessels. And I was like, well, that's totally different than these IL-4. Like, that's not the same as what I'm talking about. I don't have any tumors in my tissue repair setting, so that doesn't help me at all, right? So I started doing just fundamental experiments in vitro with human macrophages pushed to these different phenotypes to test various aspects of angiogenesis. Turns out M1 macrophages are very potent at stimulating angiogenesis. But so then I'm like, okay, why is it that everybody thinks that M2 macrophages are so angiogenic when it's these M1s that are clearly the best at it? And then I found that if you look at later stage processes in angiogenesis, that is when the M2 macrophages started to show some promise. So the M1 macrophages were very good at initiating angiogenesis, but they were not good at stabilizing growing blood vessels. You needed the M2 macrophages to do those stabilization processes later. And that explains why everybody thought that M2 macrophages were so angiogenic, because if you were doing like an animal study or even a human study of wounds that were healing or tissues that were repairing, and without those M2 macrophages at a later time point, you would not have successful blood vessels. But nobody was looking at the early time points, because why would you do that? You would look at a later time point to wait for the blood vessels to form, and then you'd say, oh my gosh, look at all these M2 macrophages. And that is what happened. But if it turns out now people have done these experiments, including us, if you inhibit M1 at the early stages of any wound or tissue, that inhibits angiogenesis. So our proposed model that we're still teasing out and proving that this is what's happening is that M1 macrophages initiate angiogenesis, and then M2 macrophages stabilize angiogenesis. Now, the plot thickens even more because it turns out the M2 macrophages are super diverse. And as you started this off by saying, like, and I did too, there already was M2A and M2C, but then the more we study it and the more we do more sophisticated techniques like single cell analysis, the more we realize that there's like many phenotypes that could all be described as M2, especially in vivo. And it's very, very poorly understood what each phenotype does in the context of tissue repair. But coming back to the original goal, which is make biomaterials that promote tissue repair, we have to know which phenotype is the one that promotes tissue repair, because once we know that, we'll just figure out what drug or cytokine or stimulus makes that phenotype, and then we get our biomaterial to do that. So that we're still at that point. We're still trying to figure out what is the phenotype that we want to promote for tissue repair. And we're starting to appreciate that that's going to differ in different injuries and different time points of injuries, so it's gotten a lot more complicated, but I think the strategy is making a lot of sense, which is fundamental basic science to understand which macrophage phenotypes are beneficial for which aspects of tissue repair, and then design biomaterials and drug delivery strategies to promote that phenotype at the right time and at the right setting.
And you have some fascinating IP that you've been putting together the last couple of years. These really neat scaffolds that guide, as you're saying, that conversion. You may have some IL-4 in one area and then IL-10 in the other, and helps with this. Do you foresee, is the main output in case of these going to be sort of the ex vivo created biomaterials that are implanted? Do you foresee other, small molecule drugs, other therapeutic interventions that may be able at some point to do this in vivo? What are some of your visions there?
Yeah, we're pursuing all of the above in tandem, because I think all are going to be useful in different contexts, So when you go, in engineering, we're taught to start from the problem and then design the solution to the problem. In basic science, you kind of start at needing more fundamental understanding. So in biomedical engineering, we meet in the middle, right? So, but when you're getting to a problem, let's say chronic wounds, right? It's a diabetic foot ulcer or a venous leg ulcer. They already use wound dressings, and wound dressings are very important to keep the wound clean, to prevent stuff from getting inside it, hopefully to facilitate healing. So in that case, it makes a lot of sense to design a biomaterial that is off the shelf, that you can just take off the shelf and put on the wound. The other reason why that makes sense is because the the healthcare system is really set up for cheap devices to be applied to chronic wounds. It doesn't support very expensive strategies very well, for better or for worse. I think for worse, actually. But working within the confines that we have, the way that healthcare works, at least in this country, you really need a pretty cheap product for a chronic wound in order for it to be successful. So that means you need a pretty simple product, but hopefully one that actually works. But now, if you're talking about something that you are definitely going to die from, if you don't have a treatment, like let's say you've got severe COVID-19 or severe flu, if there is a pretty expensive therapy, but we know will save your life or save your quality of life for the rest of your life, that can tolerate that. That market can tolerate that. So then you could have a much more sophisticated, complicated experiment or strategy. And so for those types of applications, that's where we're really pursuing cell therapy strategies using monocytes, which are they're like the precursors of macrophages, and macrophages themselves as cellular therapies to treat those patients. And we're still using biomaterials to engineer those cells, but it's working. It's like a biomaterial together with the cells as a strategy instead of just a, off-the-shelf biomaterial.
Cool. Yeah, I was looking actually at this really recent paper that you collaborated on, where you were actually looking at the human hair follicle mesenchymal cells, and we always hear about the sort of mesenchymal stem cells. They might not be extremely potent in terms of regeneration, but they got this really neat immunomodulatory capability. Got me thinking about okay, the interesting combinations here with what you're doing. And I don't know if you could say a couple words. I know that was like yesterday. You probably published that, but
no. But you're exactly right, because this has been very influential in my thinking about cell therapies. Because MSCs, mesenchymal stem cells or mesenchymal stromal cells, they have been used in thousands of clinical trials to promote tissue repair and basically to modulate. They've been used in all sorts of things: tissue repair, cancer, infections, like everything. And they're a really beneficial cell type. But when people started figuring out why they are so effective when you inject them into somebody's body, the reason why is because they modulate the immune system, right? So like you can skip that part and just go straight to modulating the immune system if you know how, right?
Gotcha.
And the reason why you would want to skip that part of isolating MSCs is because they are a pain to isolate from patients, literally. So the way that they were first discovered was isolating from the bone marrow. So you still have strategies where people are using these enormous syringes to extract bone marrow from people's pelvic crest bones. But more recently, people have discovered that you can get MSCs from like adipose tissue, which is easier to harvest from a patient. And in this paper that you're referring to, we showed that you can isolate them from the human hair follicle. So even from human hair, you can get these MSCs. So that's obviously a much easier way to isolate them than the pelvis. And so importantly, in that paper, we showed that they too modulate the immune system. So that could be a new source for MSCs. But I still think we don't need the MSCs at all, because we now know how to modulate the immune system. So we can just skip that MSC part and go straight to the immune system.
Get them out of there.
So that's what we're trying to do.
Awesome.
Right. And also the thing about monocytes and macrophages is that they're just circulating in the blood. So they're really easy to isolate from a patient. You just take a unit of blood, as if, which is what happens when people are donating blood all the time, every day, and you just isolate your monocytes, and then those monocytes can be differentiated into macrophages very easily.
Really cool. Garrett, one other place I wanted to go with you. You started off, you were talking about cartilage. And then we went to bone, and then you had this realization, this is broadly applicable to all sorts of regenerative medicine ultimately. And it got me thinking, we talk a lot on the show about aging and sort of this theme of immunoaging, inflammaging, as some call it. And we had a couple months ago, we had Judy Campisi on talking about sort of senescence cells, the senescence secretory phenotype. And once again, here's this interesting cocktail of stuff that at the beginning we thought, oh, this is all bad stuff, but now they're beginning to realize, we got some inflammatory stuff in here, but we got some other beneficial things in here that. any interesting insights in terms, obviously you got your plate is full right now, but any broader insights that you've come upon with regard to just systemic aging and some of the directions you may take some of this knowledge in the future?
Yeah, great question. And I'm so interested in this. I have a very exciting collaboration happening right now with Lisa Kuhn at the University of Connecticut, who I also recommend you reach out to for your show.
Cool.
And she is exactly focusing on what you're talking about, which is aging and senescence in the context of bone repair and making biomaterials that design for those patients. So instead of designing for a healthy mouse or even a healthy person, she's really starting from the patient. You know, a lot of these patients that are undergoing bone repair surgeries are elderly, and probably have other comorbidities, but the aging itself has such a huge impact on the immune system and your ability for tissue repair. So that's her focus right now. What I have learned through collaborating with her has been really interesting, because you hear about inflammaging, and what that means is that you've got elevated levels of inflammation just like in your body as you get older. But the surprising part that Lisa and I found and other people found is that when you give your immune cells, when you give immune cells like macrophages from elderly patients a pro-inflammatory stimulus, although their baseline levels are higher levels of inflammation, they actually failed to mount an appropriate inflammatory response to that stimulus. So in other words, if you take a macrophage from a young person and you give it an inflammatory stimulus, it spikes its inflammatory processes and then it downregulates it. And as I just told you over the last 45 minutes, that those inflammatory responses are actually critical for initiating healing, especially angiogenesis. But if you take a macrophage from an aged person, first of all, its baseline level is a little bit more inflammatory, but then when you give it that stimulus, it fails to spike as much as a young macrophage does. So the fact that it's not actually spiking enough is really important, because that spike is critical for initiating healing. So it actually adds some complexity to the problem. It's actually maybe not too much inflammation, but too little inflammation in different contexts. So in aging patients, it looks like you have chronic low-level inflammation, which is bad and leads to collateral damage throughout your body. But then you fail to mount a robust inflammatory response in response to infection, a vaccine, a tissue repair. So all these places where you need a robust inflammatory response, it's actually less in aging patients. So that's a problem too. So Lisa and I have been designing biomaterials that are pro-inflammatory for a short period of time to try to overcome that weak inflammatory response, but then ushers the cells into a reparative stage later. A sequential drug delivery strategy.
Really cool. Really cool. You gotta, I take my hat off to you. You have a lot on your plate, but this is truly a fascinating domain. And you know, the complexity of it, as I said at the beginning, it's just we don't normally think about the complexities of the immune system at this level, but there's just so much going on, and it's exciting to see you working on all this. One last thing I want to ask you about. I know you just wrapped up one of the immune modulation and engineering symposium. I watched your presentation from about 5 years ago, which was entitled "Building Bridges: Valuing Interdisciplinary Research," and you talked about the clashings of perspectives early on. What did you run into at the current symposia? What areas? Not that you're not focused on everything, but what other stuff did you come across in the collaborative interdisciplinary domain of immune modulation and tissue engineering that gets you excited for 2022, 2023, and so forth?
Yeah, thank you for bringing that up. So yeah, this is an initiative that a bunch of us at Drexel are organizing, which is annual symposia called Immune Modulation and Engineering Symposia. And the reason why we call it that is to be inclusive to everybody who thinks they're an engineer or is not an engineer, or whatever. So the point is to bring together people from different disciplines and different perspectives. And the reason what spawned that is that sometimes, immunology and engineers are trained so differently, and there's so many classes and everything that has to go into getting your degree in either engineering or immunology, that there is often not time to cross, learn, to even to talk to people from these different disciplines. So the goal of the symposium was to just bring together people from these different disciplines and show that each side has skills and perspectives and expertise that would be beneficial to the other. And we believe that with repeated introduction to each other's work and each other's way of thinking and way of talking about things, it'll elevate science on both sides. So it'll elevate the engineering approaches, and it'll elevate the science approaches. The other thing that we try very hard to do in that symposium, beyond having diverse voices in terms of training and discipline, but also in what their current profession is. So we make sure to have a lot of people who are clinicians who actually treat patients, and also a lot of people from industry who are actually making real products that go into patients like right now. Because though just having that different approach, even if your background is in immunology, but if you're in academia or you're in an industry, you have a completely different perspective on the same problem. So really the goal of this symposium is just to bring people together who have different perspectives on the same problems, just to try to make everything better and get people talking more. So it's been really fun, and there's all sorts of different topics that you can focus on in a multidisciplinary symposium like that. So we're just working on the agenda this year, and we're talking about having a session on the gut immune system axis, on neuroimmunomodulation, on designing therapies for immunotherapies for a pediatric population, and how that might be different from an elderly population or a young adult population. So even if you take even just immune modulation and engineering, which sounds like a very specific topic, even within that, there's so many different ways that you can learn about it. So it's been fun.
Absolutely. Sounds very exciting. As does everything you talked about, Karen. It's really a fascinating portfolio. Really rooting you on for not just the clinical translation, but everything else that's coming down the pike in terms of the basic research. For everybody that's going to be listening to this episode on the podcast networks or watching on the YouTube channel, you've been listening to the amazing Dr. Kara Spiller, Associate Professor, Biomaterials and Regenerative Medicine Laboratory here in the city of brotherly love at Drexel University. Kara, I want to thank you for taking the time out of your schedule to talk to us for a little while about these teams. Obviously, thank you for everything you're doing there. And as we say on this show, thank you for helping to usher in a better tomorrow through your work. It's a really fascinating story.
Thanks so much. Thanks for having me. This was great.